So I'd first like to thank all the organizers for the kind invitation to speak here. As always, it's a great pleasure for me to visit KIAS, although it has to be virtual this time. So today I'd like to tell you about how some of the quantum gravity constraints are realized in string theory. The talk will base mainly on these series of works, which I have been doing for the past couple of years in collaboration with various colleagues, Wolfgang Rehe and Gulli Lockhart at CERN, Timo Weigand and Daniel Klauer at Mainz, and Max Wiesner at IFT. Let me begin by discussing a couple of central notions first. Firstly, quantum gravity constraints, or QGCs for short, refer to any consistency constraints that quantum gravity is believed to impose on general grounds. Note that the word believed here is italicized, emphasizing that it's a belief or a conjecture, even if there exists a physical intuition behind them. Secondly, it's all going to be about effective field theories, or EFTs for short. EFTs are simplified by integrating out high energy degree of freedom. Then we ask the question as to what are the possible EFTs of UV quantum gravity theory. One famous example that must be okay in this context is the standard model plus general relativity, at least below a certain energy scale. But of course, there are zillions of other EFTs with gravity that are as consistent as the standard model. And in this talk, we'll be caring for all of them. Specifically, our goal is to understand quantum gravity constraints in the context of string theory. The quick key question being the like this: does string theory know about those constraints or conjectures? Of course, string theory better know of them, consciously or not, to be a valid quantum framework for gravitational and gate dynamics. And if the answer is indeed yes, we may also want to understand how. String theory has a plethora of vacua, which leads to many string effective field theories. In this context, there arises the distinction of the so-called landscape from the swampland. The latter refers to the set of EFTs that cannot be completed to quantum gravity in the UV, and the former is the complementary set. Here's the usual Venn diagram description of the theory space, which splits into the landscape and the swampland. But we must be reminded that there are, all the theories here are all EFTs at a given energy scale. So to be very precise, we have to also imagine an additional axis for the energy scale, at the top of which lies the quantum gravity theory, which for our purposes can be thought of as string theory. Then once again, our pressing question is how to distinguish the two sets. And you can think of the quantum gravity constraints as providing a set of guidelines for this. So what kind of evidence do we have for the validity of those guidelines? The evidence comes in two types, largely. One is based on a general quantum gravity argument, and the other is based on a direct test. Each has pros and cons. The former type is rather general and model independent, but only provides heuristics. The latter type, on the other hand, is rigorous because an explicit and precise test is going to be made, but it tends to be model dependent. What you do is to test them for a given specific effective field theory, if you can ever do the required hard computations for that theory. In this talk, we will focus on the latter type evidence, but in a manner that saves us from its disadvantage. Hardness we must face, of course, but we will try to make it as convincing as possible by addressing the conjectured constraints for a whole class of general string effective field theories. Here's a subset of conjectures in the literature, and this talk will address all of this, and in particular, their interconnections. So let me say a few words about each of them in turn. Firstly, no global symmetry, which is one of the earliest conjectures, indicates that the coupling constant G of a gauge force cannot become 0 in presence of gravity. Second, the completeness says that the charge spectrum has to be complete in that at every charge value, there must exist a particle with that charge. Third, the so-called weak gravity conjecture claims in its strong form that a lattice amount of charged particles must obey a certain charge to mass ratio bound of this form, where the lower bound mu here is an order 1 constant in Planck unit. This inequality indicates that gravity is weakest, at least for these particles, and that's the reason for the name. Just for future terminology, I will call any particles saturating this inequality extremal, and those that strictly obey it super extremal. Last but not least, the distance conjecture claims that if you deform the theory too much, then there must arise an infinite tower of Lie states with their masses suppressed exponentially. Let me emphasize that all of this, except for this first one, claim the existence of a certain tower of particles, which is in fact a really strong claim. Now, we are interested in seeing if and how each of these constraints is realized in string theory. And for this purpose, let's say we try to violate the first one in a given string effective field theory by appropriately deforming its parameters. Then what I will show in this talk is that a light tower must indeed arise in this situation for whole classes of string EFTs, in fact, rather than for a specifically chosen model. Interestingly, we will see that string dualities together with geometries are at the core of these conjectures. Before entering into the details in the next couple of slides, I will first get you a schematic picture of how the general stories would go. To be concrete, I will illustrate with 5+1 dimensional effective field theories obtained as a minimally supersymmetric compactification of type 2B string theory, also known as F theory. So for the next 5 minutes or so, the internal space for the compactification will have real dimension 4, and I will denote it as B sub 4, where the 4 is the real dimension of the internal space. As I said earlier, we will take the gauge coupling to be very small with gravity kept fixed. Very importantly, the Planck scale and the gauge coupling are both determined by the internal geometry. Specifically, the former is given by the volume of the entire internal space P4, while the gauge coupling G is inversely proportional to the volume of a certain two-dimensional subspace S2. Then our physical question up here is translated into this geometrical question. What happens if the surface S2 stretches inside a fixed volume B4? Our answer is that another curve C2 inside B4 must shrink. Why? Just to give you a rough intuition, let's imagine deforming a fixed area rectangle. Obviously, if one side was to stretch like this, then the other normal side would have to shrink. And in a sense, my claim is a generalized version of such a simple fact. So once again, we take a weak coupling by stretching the blue surface S2, but as we want to keep the B4 volume fixed, we have to squash the whole thing vertically, then inevitably the red surface C2 shrinks. What about the physics of all of this? We can consider the three branes which are present in the theory, wrapping around this internal surface C2. This then leads to an effective string in the external, in this case, 5+1 dimensional spacetime, which in fact turns out to be an E8 times E8 heterotic string. Now, the tension of this string is proportional to the volume of C2, which goes to 0 in the weak coupling limit, as I have just claimed. So the effective heterotic string becomes tensionless, And therefore, the mass scale of its quantum nodes will go to 0 as well, leading to a light tower as predicted. And furthermore, upon some detailed analysis, one can also confirm that this tower also satisfies all the specific properties required by various conjectures, which is very nice. So what we are doing is to deform the effective physics so that the gauge coupling becomes very small by appropriately deforming the geometry. In other words, in the parameter space of the B4 geometries, our starting point is here at type 2b, and upon moving along a certain path, we are ending up with the E8 heterodyne point. And as you all know, this is what string duality is all about. So over the past couple of years, we kept confirming this general feature in various different string setups. And it was,
can I ask
yes?
you one question?
Sure, yes.
Okay, so are you assuming some specific B4 or it's for generic?
No. That's a very good question. It is actually a model independent analysis. So maybe it wasn't clear from the context, but I will clarify this later. But this is going to be model independent. Everything will be for really arbitrary based B4.
So you are also taking into account the P2 base or Enrique surfaces and so on. Okay,
very good. So you know, the starting point was, okay, my statement is all about weak coupling limits. So as long as the geometry or the background admits a weak coupling limit by appropriately deforming it, then I can say this. For example, P2, Enrique, all of these, Enrique, okay, maybe I have to think more, but at least for P2, for sure, I can say this. This doesn't admit a weak coupling limit.
Oh, okay, thank you.
Yeah. So for any background that admits such a weak gauge coupling limit I described, then this results hold. That's the claim.
Okay, so all the gauge groups so over the P2 base will have always a strong coupling.
So I'm fixing the Planck scale because I'm fixing the overall scale of overall P2 size. Mm-hmm. Then P2 case, as you know, there is only one Keller parameter, so you cannot tune the other divisors there. Mm-hmm. So that's the logic.
Okay, thank you.
Yeah, thanks. So yeah, so I was just gonna give you the upshot of all the stories. So yeah, I was gonna say that it was always through the emergence of a dualized string that these quantum gravity constraints are fulfilled, and we've studied quite a few cases, different settings, and by now it has become my strong belief that duality and geometry are indeed the key to many of these constraints via the emergence of a Lie string. In this talk, I will be focusing on this particular path where the relevant duality is between F theory and heterodyne theory. We have studied the 60 and the 40 situations, both with minimal supersymmetries. Of course, the latter is much less controlled and accordingly much richer in dynamics. The main goal of this talk is then to verify the conjectured constraints in this more complicated 4D setting. However, I myself find that comparatively the 60 analog is often very helpful. So in various places of the talk, I will also present the 60 counterpart stories, hoping that this doesn't mess up the flow of the talk. While these 60 stories can be thought of as a review, they will also clarify the genuinely new features in 4 dimensions that make it much more interesting and non-trivial there. So that's the end of my long introduction. Let's now get a bit more serious to flesh out this schematic picture, which has been discussed so far. Here is the outline of the actual talk. I will start by carefully setting up the arena. The main physical object in scrutiny will be solitonic strings in 4D F theory. So I will first spend a few slides to remind you of some rudiments of F theory before getting into part 1. In part 1, I will first address the connection between elliptic genera and Gromov-Witten invariants, as well as their modular behavior. And then I will illustrate all of this in an explicit model with a U1 vector. In part 2, I will switch gears to address weak gravity conjectures in 4 dimensions, together with the other affirmation constraints, which will naturally appear along the way. as I have already sketched, upon taking a weak gauge coupling limit by deforming the geometry, we will see that a tensionless string necessarily appears, of which excitations will bring about a tower of particles, which in turn will satisfy the weak gravity relations. For the last step to work, it will be crucial that the elliptic genus is a quasi-Jacobi form, which will already have been explained in part 1, hopefully. So that's the rough plan. Let's now get this started. Okay. So a capital D-dimensional F theory is the type 2B string theory on a complex small d-fold BD with a varying axial dilaton profile. Here, a capital D is 10 minus 2 times small d. To avoid confusions, let me point out this change of notation actually. Hereafter, I will constantly stick with the language of complex algebraic geometry. So in particular, any subscripts for manifolds, D here, for example, will always denote complex dimensions rather than real dimensions. Now, the dilaton profile can be specified by an elliptic fibration over BD, of which total space is a Calabi-Yau D+1 fold Y. And the projection map I will denote as pi. Then the gauge fields arise from 7 branes on a divisor B of BD, whose class we know how to compute in a given background. Apologies for using too many B's, in fact. Actually, there will have to appear quite a few more B's. I hope this won't distract you, but in case it does, please ask me at any time. As for the gravity and the gauge dynamics, their couplings are respectively given as the volumes of the internal space BD and the gauge divisor B. In this talk, we will be especially interested in the U1 gauge dynamics for the purpose of addressing weak gravity in part 2. But many of our results do apply to non-abelian cases and also to several U1s. And because we will focus on the interplay between these two dynamics, the moduli space in question will be the Kähler moduli space of the base. And I will elaborate on this in part 2. The geometric origin of U1s in F theory is the non-zero sections S in addition to the trivial section S0. One can define the so-called Shiedo morphism that maps a section to a divisor class in the total space Y, such that these defining properties are satisfied. Then schematically, the map takes this kind of form where pi, I remind you, was the projection map from the Calabi-Yau to the base. I will sometimes write the Shiedo image as just sigma, omitting the argument S here. So like in here. So sigma sometimes will mean the image of the Shiedo map of a section. Note that I'm using a circle for the intersection in the Calabi-Yau D+1 fold, while a center dot will be used for the one in the base later. Now, via the duality with M theory, a U1 vector arises from expanding the M theory 3 form over the Shiedo image. And its inverse gauge coupling is given by the volume of a certain divisor B, defined like this. And this is known as the height pairing divisor. Importantly, when non-trivial sections are present, there arises a fibril curve CF, which is homologically independent to the full fiber CE, as I depicted here in this picture. And these two curves, CF and CE, intersect with the sections like this. And accordingly, the curve CF is going to carry a U1 charge because it intersects with the Shiedo image. Now to the fluxes. Supersymmetric fluxes lie in H22 which we can decompose into the so-called horizontal part, the vertical part, and the remainder. To study gauge fluxes, we will consider the vertical fluxes, which are just products of 1-1 forms. Then the genus 0 invariants are computable via mirror symmetry for 4 folds, under which the horizontal fluxes and the vertical fluxes are exchanged. Now, imposing 4-dimensional Lorentz invariance will tell us that the fluxes must obey these transversality conditions. They turn out to give the subspace of H2 to vert spanned by the classes of this form. Here, sigma was the Shiedo image, and the alphas here are the basis 1-1 forms on B3. This subspace is often denoted by subscript -1. For some reason, I will touch upon later. In fact, any vertical flux has a decomposition into these 3 sectors. They are called 0 fluxes, -1 fluxes, and -2 fluxes. However, in 4-dimensional F theory, we will only care for the so-called transversal U1 fluxes or -1 fluxes. So the base divisor B, when wrapped by D7, leads to a 4-dimensional gauge multiplet. And similarly, a base curve CB, where B is for base, when wrapped by D3 brane, will lead to a 4-dimensional effective string. The worksheet theory of such a solitonic string is then obtained by reducing the D3 dynamics along CB, and turns out to have 0-2 supersymmetries. Furthermore, if CB intersects the gauge divisor, then 3-7 modes are present, charged under the 4-dimensional gauge group. Then in the end, the topology of CB embedded in B3 will tell us about the type of the resulting strings. In fact, we will mostly consider base 3 folds that admit a rational fibration, which I'll denote as P, over a 2-fold base B2 of its own, and turns out to have okay. So I will denote the genetic fiber of this rational fibration C0. So throughout the talk, when I call C0, it is the genetic fiber of the rational fibration for the 3 base B3. Then, okay, so in this setup, so obviously the normal bundle for C0 inside this 3 base B3 is going to be trivial because it's a fibration, and the topological configuration of this embedding enables us to identify the corresponding string as the 4-dimensional heterotic string. Of course, the fibers may degenerate at non-generic points. Like in here, it degenerates into a pair of rational curves. And if, for example, if these two curves, C1 and C2, have normal bundles O-1 plus O, then the corresponding strings have an interesting feature analogous to 6-dimensional E strings, as most of you will be familiar with, and we may call them 4-dimensional E strings. In this talk, I will oftentimes restrict to the special cases where CB is in fact fixed to C0. This is for a direct application in part 2, but let me emphasize that most of the general results of part 1 will also apply to the non-critical strings like E strings and so on. So having set the arena up in F theory, let me finally start part 1. I will first discuss elliptic genera, and then we'll later explain their connection to Gromov-Witten theory. So elliptic genus of a 0,2 string is defined as an index like this, where the 2 figurative parameters Q and Xi distinguish the states with distinct energy levels and the U1 charges. One of the basic properties of the elliptic genus is that it only gets contributions from the sector with HR equals 0. For heterotic string, however, non-trivial terms in that can be level matched by right movers. to give physical particle excitations of the four-dimensional string in the space-time. Therefore, computation of hedonic elliptic genus will play a special role in that it provides certain information about the spectrum of the space-time theory. And that's why it will be important in part 2, but that part will come later. For now, let me point out a couple more important properties in our F-theory setup. Firstly, expansion coefficients of 4D elliptic genera are interpreted as certain Gromov-Witten invariants on the elliptic target fourfold. Secondly, a well-defined behavior is expected under modular and elliptic transformations, at least naively. Let me now try to elaborate on these two properties in turn. In fact, I will first review the perhaps more familiar 6D story. We consider a 6D F-theory on S1 and the solitonic string associated with a given base curve CB. The string, once wrapped on the circle with winding 1 and momentum n, corresponds in the phi d M theory dual to the M2 brane wrapped on CB plus n times the full fiber. Then the duality tells us that the elliptic genus of the 6D string encodes the BPS invariant for the M2 particles in the M theory. So to be more precise, because we consider a U1 refined elliptic genus, we expand it in two figurative parameters, Q and Xi. And I denote it as ZY3CB by specifying the elliptic Calabi-Yau and the type of string. Then the expansion coefficients, the capital N's, are the Gromov-Witten invariants on the elliptic Y3 for the curves C sub n R, which are CB, the base curve, plus n times the full fiber, the elliptic fiber, plus R times another fibroid curve, CF, carrying a U1 charge as already defined. And the fugicities tau and Z are going to be the volumes of the CE and the CF on the M3 side. Note that there is a shift by a certain 0-point energy given in terms of this topological intersection. Here, K bar is the anti-canonical class of the base, in this case, B2. So in the end, up to this 0-point shift, the generating function FCB of the invariants is going to be identified with the elliptic genus of the, so to speak, CB string. Furthermore, FCB is computable via the good old mirror symmetry techniques for threefolds. Now, turning to 4D, we propose, by analogy with threefold cases, that the four-dimensional CB string elliptic genus has its expansion coefficients n's, given by these enumerative invariants again. They are the genus 0 invariants on the elliptic fourfold Y4 now, or for the 1-point fixed curves C and R, again the C and R here, with respect to a G4 flux. Once again, the generating function FCB, now also with flux G, is computable via mirror symmetry for fourfolds, and the elliptic genus is again identified with this generating function up to a similar vacuum shift. So, okay.
So why is this just a proposal?
Oh, okay. So it is a proposal in that, so.
I mean, in certain parameter limit, I mean, in which you expand, just like in the previous case, can't you just relate it to, can't you just relate the wrapped M2 brane indices to this Walsh instanton contribution, which will be directly what is Gromov-Witten invariant?
So I think this kind of story will exist, I think. I was saying that this is a proposal because, I was just naively generalizing this 6D result by promoting this threefold invariant to the fourfold invariant. But in defining the fourfold invariant, you have to also define a four form because of the dimensional region which I was going to mention, but maybe I don't have to. But there are lots of things you can do for the fourfold invariant, and this is, of course, the most obvious kind of invariant you can define in the M-theory background. And I think in the end, there will be some rigorous theory that can be made. But I was saying that this is a proposal in this naive geometrical sense. And then we also check this for the zero mode at least. So I think it will be true.
Okay, thank you.
Yeah,
thank you.
Thanks. Okay, let me forget about these math remarks. I mean, these invariants are defined a bit more in a bit more complicated manner than the threefold analog, but they can be defined, and these are the natural invariants to think about. So now to the modularity. Again, back in the 60s story, the elliptic genus is known to be a Jacobi form up to potential quasi-modular E2s. Just to quickly remind you of a Jacobi form, as many of you be familiar with, it has two defining behaviors under these SL2Z modular transforms and under these so-called elliptic transforms. And the two integers appearing here and there, the W and M, they are called its weight and index. Another quick reminder is that the ring of holomorphic Jacobi forms is finitely generated, which is a very strong result. The generators are the two famous Eisenstein series E4 and E6 with weights 4 and 6, as well as some three specific Jacobi forms with indicated weight and indices. Now, on general grounds, it is expected that the elliptic genus has a well-defined weight and index. For a string in capital D dimensions, the expected modular weight is given like this, which for a 60 string is -2. Similarly, for the elliptic index, the Toft anomaly calculation leads to this formula in terms of the intersection between the gauge divisor B and the base curve CB in question. Finally, the appearance of E2s is expected if CB can split. In the Hedderodi case, for example, the base curve is the rational fiber C0, again, which splits on a block locus into a pair of E-string curves, as I depicted before. And in such a situation, the Hedderodi elliptic genus does involve E2s famously. Then the elliptic genus is not modular in a strict sense. Such a modular anomaly is well known to trade with a holomorphic anomaly, as Boris Piolin also mentioned in his talk on the Monday, I think. But we won't be delving into this in this talk. Okay, so this modularity business has been very firmly established in the 60s setup, and in the past decade or so, a lot of applications have appeared. But much less has been explored in 4D. Part of the reason, I think, is that the 4D elliptic genus is not Jacobi in general, not even modulo E2s. So it's much more difficult to control. But we still have an expectation for the weight, which is -1, and the expected index is, again, this topological intersection from the Toft anomaly. Recall that even a 6D elliptic genus was not Jacobi in a strict sense, but we could control it well with the aid of E2s. It turns out that in 4D, that is not enough, and something drastically different is to happen. And our proposal is the following. In the 4D setup, there can, in general, appear a derivative sector, which completely breaks the Jacobiness. Specifically, we propose that the elliptic genus decomposes into these two parts, the z sub -1, m, and the C derivative of z sub -2, m. These two z's here are individually genuine Jacobi forms, again, modular E2s. In fact, we can say much more about these two. They are given by this kind of ratio, where the numerator is a holomorphic Jacobi form and the denominator ansatz is based on the pole structure. Importantly, the numerators for a given weight and index pair have only a finite set of undetermined coefficients because of the crucial property that the ring of holomorphic Jacobi forms is finitely generated.
Excuse me?
Yes, yes.
Can you at least motivate why this derivative sector term appears in 4D?
Okay, I will say some words about this, at least from the geometric perspective. But so I prepared some slides for that, actually. If you could wait a little bit, I will tell you about it.
Okay, thank you. Okay.
Yeah. So So you can think of this proposal as providing a concrete computational strategy for a given solitonic string in a specific background. What do I mean by this? Given a specific compactification, we can compute enough low-degree invariants via mirror symmetry techniques. Then, using them as an experimental data, the numerator ansatz can be solved for the finite set of parameters. And this way, we will be able to obtain a complete closed form expression for the elliptic genera. I will shortly illustrate all of this with an explicit example. Before getting there, however, as Seung asked, let me say some words about how this derivative structure arises at all. So once again, let's suppose our base threefold B3 is rationally fibered over a twofold B2. And again, I will denote the projection map by P. For concreteness, we'll assume that the base B3, the 3 base, is a blow up of a non-degenerate fibration along a single curve in B2. Over this locus, the fiber C0 splits into C1 and C2. Here, the fibration of the ladder curve C2 is the blow-up divisor, which I will denote as E, and I will denote the exceptional section as S minus. So this is a section to the rational fibration within the base B3. The reason why we assume such a rational fibration is, again, because we are going to be interested in the heterotic elliptic genus. So with this period in mind, we will set CB as C0 for the rest of this talk. So suppose we've constructed a certain U1 model over a 3 base of this particular type by specifying an elliptic fibration to make it an elliptic fourfold. We also choose a Lorentz invariant flux, which is going to be a linear combination of these basis fluxes. Here, sigma is again the Shiedo image, and the alphas are the basis 2 forms of B3. And in this setting, these basis 2 forms of B3 can be taken, for instance, as the section, the blow-up divisor, and the pullback divisors, where the gammas are the basis divisors of B2 base of B3. So what's the geometric origin now of our proposal? To clarify this, we need to study the invariance on Y4 for the curve classes C sub NR with respect to these basis fluxes. So we need to understand these invariants. So, okay, I think I'm doing well, fine. So let me give you a little bit of details of how this derivative sector arises from the geometry. So in fact, I must say that this slide is going to be the most technical slide. And if you are happy to accept our proposal about the derivative sector, you may just close your eyes for the next 3 or 4 minutes. If not, please bear with me. I will tell you some details. So the idea is to consider 2 types of special fluxes in turn, which when combined span the entire flux space. The first type is GIs of this form. This is a pullback type, where the alphas for the U1 fluxes are chosen as P star, where P was the projection to the B2, P star of the divisors in B2. Note that such a pullback divisor, B gamma I, is itself a C0 fibration because it's pulling back certain curve in B2 to B3. Therefore, the fourfold invariant is going to be reduced to this threefold invariant, where Y3I is the induced elliptic fibration over this rationally fibered surface P star gamma I. Here by Abusor notation, I'm using the same symbols, sigma and C sub NL, for the classes appropriately restricted to Y3I. Then by the so-called divisor equation, the marked point, which still exists here because you're inserting some class here, this marked point will be removed by introducing this kind of prefactor, sigma dot C sub nr. And because C sub nr includes R many CFs, and because CF carries a single unit U1 charge, this will spit out R. And this means that, and R is nothing but the power in Xi. So you are taking essentially the derivative with respect to Xi, and then you are getting R factor, and then in order to raise the power by 1 again, you need to multiply by Xi. And that's how this Xi derivative arises. Here I have combined all these GIs to make it a most general flux of this special type. So because of the linearity of this fourfold invariant, you can linearly combine these fluxes, and you get this derivative structure, pure derivative structure for this kind of special fluxes at least. So another type of special flux is what we dubbed in this work as quasi-modular fluxes. A flux is called quasi-modular if the base divisor D appearing in this flux obeys this kind of constraints. So this kind of constraint is to be obeyed for each pullback class P star gamma from the base to base B2. And for such a special flux, it has been argued in this work that for the elliptic genus is in fact a genuine Jacobi form of the expected weight and index. So of course the idea now is to combine these two fluxes to make a most general flux. As I said, these two fluxes happen to span the entire flux space. Therefore, from linearity, again, we finally arrive at this proposed general structure. There is some part which is genuinely Jacobi, and another part which is just a derivative of a genuine Jacobi of weight 1 lower. Right, and in fact, I must say that in getting to this conclusion, I have assumed that the 6-dimensional Z here is a weight -2 Jacobi form. This is physically clear if Y3 is Calabi-Yau itself, then you can imagine F3 background based on Y3, then you can think of the corresponding string in that 6D theory, then this Z is going to be the elliptic genus, and therefore this is going to be Jacobi. However, in general, Y3 does not have to be Calabi-Yau, and in such cases, I do not know of a physical way of assuring its Jacobiness. Even when Y3 is not Calabi-Yau, however, in all our explicit examples analyzed, we have observed that ZC0 on Y3 is indeed a Jacobi, and also we have observed that it encodes the fourfold invariance now with respect to a yet another -2 flux, which is determined by the starting -1 flux encoded in D by this formula. These observations are in complete agreement, in fact, with the math conjectures given by Oberdieck and Pixton in 2017. In fact, these people conjecture that for the elliptic genus, well, if I rephrase it in terms of physics, is a quasi-Jacobi form. And the derivative structure we have proposed manifests this quasi-Jacobi nature. For the sake of time, however, I won't discuss the details on quasi-Jacobi forms. Let me nevertheless point out once again that the C derivative is a manifestation of the quasi-Jacobi nature. So it has been rather abstract by now. So let me illustrate all of this in an explicit fourfold example. The 3 base of our choice is dp2 times p1L. Here the dp2 is a blow up of the Hertzsprung surface F1, which is a fibration of rational curves P1F over the base P1H. Then we will take this P1F as the C0 of the fibration P, of which twofold base is now P1H times P1L. The 1-1 cohomology of B2, which is P1 times P1, is of course spanned by these two P1 factors, and that of B3 is spanned by the two pullback classes and the blow-up divisor E, and the section S minus. Here I've in fact taken certain combinations thereof, but any basis will do, so it doesn't matter. As for the elliptic fiber, we will use this specific particular elliptic curve of which ambient twofold has this GLSM description. The reason is because a rank 1 amount of non-zero sections will be obtained this way, as suggested by Morrison and Park. This will therefore lead to a single U1 vector in the model. Specifically, we take a hypersurface of this form where the coefficients are sections of appropriate line bundles on B3. Here appears one unfixed class beta everywhere, which we will take as 2 times k bar in this example. Then the U1 high pairing is computed also as 2 times k bar. As for the fluxes, because H11 of B3 for this model is 4, there are 4 basis fluxes whose linear combination will give us a most general flux. Here, the small c alphas are the flux parameters. Now, given that both the B3 and the fibration admit a GLSM description, we can just apply the mirror symmetry techniques to compute the low degree Gromov-Witten invariants. I skip over the details. Here is just the result of this calculation up to the 2nd order in Q. Next, we restrict to these 2 threefold hypersurfaces, which are also elliptic. And in this case, both of them turn out to be a Calabi threefold. Then similarly, we can compute the threefold invariants again by mirror symmetry, and this is a result. We will then view these expansions as the first few sectors of the heterotic elliptic genera in 4D and in 6D. Remarkably, it turns out that the 4D elliptic genus can be reorganized in this way, where Z0, 1, and 2 have these closed form expressions. Furthermore, the Z1 and Z2, which furnish the derivative sector, are precisely the unique quasi-modular completion of these expansions for Y3Is. All of this precisely fits with the claimed general structure. And in fact, our proposal also predicts the coefficients in front for this combination. And in this model, this has been confirmed as well. So having focused on the worksheet physics so far, we will now switch gears in part 2 to start discussing the space-time physics. In particular, we will address how the weak gravity conjectures are realized. If you remember what I said in the introduction, what we want to do is to take a weak gauge coupling limit and to see what happens there. So the claim I made was that there must arise an emergent tensionless string. Let me now explain why. As usual, I will start with the 6D story. This is a repetition, but let me say it again, this time in a very precise form. The key geometric statement is the following. In the weak coupling limit where the volume of a certain complex curve B goes to infinity, while the volume of the whole base B2 is kept finite, one can always find a shrinking curve C0 in B2. Furthermore, it intersects with the big curve B. Its self-intersection is 0, and it intersects with the anti-canonical curve twice, which implies that via Riemann-Roch, it's a 2-sphere. In fact, the shrinking curve class is unique if we ignore negative self-intersection curves. If we buy this, then upon wrapping D3 brane on C0 and dimensional reducing, we end up getting a solitonic heterotic string in 6D, because C0 is genus 0 curve with a trivial normal bundle. It is in fact tensionless in the limit, which according to the rule of F heterotic duality also implies that the string is going to be weakly coupled. And it carries a U1 charge because B is going to be the U1 divisor. And furthermore, this last bit tells us that such a heterotic string is unique, which is assuring. This geometric result was proven in this work in full generality. So why should such a shrinking curve exist? I don't want to bore you with the details. Let me only just sketch the very key ideas. The main task is to characterize the form of the Kähler class in an arbitrary weak coupling limit. The Kähler class in such a limit turns out to involve precisely one large parameter T associated with some Kähler generator J0. Then necessarily J0 must square to 0 because otherwise the volume of B2 will diverge. Then the heterotic curve C0 is nothing but this J0. In particular, we can show that the volume of C0 tends to 0, and in fact, at the rate of 1 over T in the weak coupling limit. Here, T was the this large parameter, Kähler parameter, describing the weak coupling limit. Furthermore, you can show easily that C0.B is going to be positive and even, and we will call C0.B as 2 times m for a positive integer m. So why is it unique? Again, skipping all the details, let me only just tell you that it boils down in the end to the intersection signature in B2. It just works out. Now, what about in 4D? Once again, we have a similar geometric result. Here is just a wordy summary. Let me just read it. In the weak coupling limit, there exists a unique genus 0 curve C0 shrinking at a fastest rate with a trivial normal bundle. Unlike in 6D, the uniqueness in 4D is only guaranteed for a fastest shrinking curve. So there can be other shrinking curves, but the fastest one must be unique. But if you think about it, that's all we need for the well-defined unique heterotic duality frame in the limit. A major new feature in 4D is that a weak coupling limit can be achieved in two qualitatively different types of geometric limits. In 6D, the Kähler class had to involve a large Kähler parameter T with the associated Kähler generator J0, and again, J0 had to square to 0. Similarly, in 4D, we will still have such a generator J0, but this now has to cube to 0. Its square can be 0 or not, because now the base is a threefold. Then, depending on whether J0 squares to 0 or not, the geometry behaves quite differently, very differently. Nevertheless, one can in the end prove that the stated property up here is shared by both classes. And that's all I wanted to say about the geometry of weak coupling limits. So what to say about the quantum gravity constraints, and in particular about the super extremal particles predicted by the weak gravity conjectures. Again, let's first discuss the 6D cases. Firstly, having characterized the weak coupling limits in the moduli space, we sit down and compute the moduli space distance d to the limiting regime from a generic point in the moduli space. We then confirm that this distance behaves as log of 2t, where t is the large parameter that appeared in the Kähler form expansion. And this indeed goes to infinity in the limit.
Can I ask a question?
Yes, yes.
This deformation, I mean, were t to infinity. How
Yes.
one can sure about stability of such a deformation?
Oh, here it is a moduli. It's a moduli, Kähler moduli.
I mean, it's moduli, but
There's no energy cost in doing this. What do you mean by stability?
Well, I mean, for instance, I mean, it could be unstable under the non-perturbative, for instance, I mean, effect, something like that.
Okay, so maybe two things. Firstly, as I said, it's going to be a modulus, so you can do this without any energy cost. And secondly, in this kind of 6-dimensional 1,0 setting, there won't be corrections to think about. Everything will be classical.
It's protected by supersymmetry?
Yeah, it's 1,0 supersymmetry.
So the supersymmetry will be enough. That's what you...
That's about the corrections. That's about the absence of corrections, but still it's a modulus here, regardless of that. So you can just deform, yeah, like this.
Okay.
I guess maybe once you go down to the 4D, then perhaps there's a substantial.
Yeah, so if you go to 4D, there will be some corrections, which I will mention later.
Okay.
Yeah, thanks. Okay, so that was the confirmation of the first conjecture. And moving to the second, because the limit is at infinite distance, the distance conjecture predicts an infinite tower of states becoming light, if you buy that. But indeed, D3 brane on the shrinking curve C0 leads to a tensionless heterodyc string, and its quantization gives an infinite tower of light particles. Specifically, the string tension is given as volume of C0, which, if you recall my geometric claim, is 1/t, where t was the large parameter. And this, in terms of d, the modular space distance d is e to the minus d. Then the mass scale of this tower is determined by the string tension, confirming its exponential suppression in d as predicted. In order to gain more information about this tower, we will now analyze the heterodyc elliptic genus, whose non-trivial terms guarantee the presence of excitations with the corresponding mode number and U1 charge. So let me illustrate this with an explicit U1 model on DP1. So it's a 60 model. The detailed construction of this example model will be, you can find it from this paper. Here I will skip over all the details and will just report on the results of our calculations. So firstly, there is an explicit model, and then the topology of this model gives the elliptic index m equals 2. Secondly, the expansion coefficients of the elliptic genus in the first few Q sectors can be calculated by mirror symmetry, resulting in these numbers. The -2 here is for the tachyon, which cannot be level matched, but all the other terms will lead to physical states by level matching. Then, based on the general ansatz for 60 heterodyc elliptic genus, we only need to determine the holomorphic Jacobi form of weight -2 and index 2 for the numerator. The set of computed invariants is more than enough for this purpose, and we thereby obtain this closed form expression. Now, what we care is the range of the U1 charge R at a given mode number n. For instance, at n equals 1, we have states in the spectrum with charges 0, 1, and 2. And at n equals 2, we have states with charges from 0 to 4, and so on. Then, with this full expression at hand, we can quickly expand it to whatever high order in Q like to explicitly check the charge ranges for that mode number. And here is the plot thereby obtained. Forgetting about the two curves, blue and the red, for now, let's focus firstly on the blue dots. So what do they mean? First of all, the horizontal axis represents the mode number n, and the vertical axis is the maximal U1 charge Qmax in the corresponding subsector of the spectrum. For instance, at mode numbers n equals 1 and 2, we have n-1, 0, and 1, and we have these blue dots at Qmax equals 2 and 4, as explicitly checked in the previous slide. Importantly, in our weak coupling limit, these states arise from quantization of our weakly coupled perturbative heterodyc string, and therefore their squared masses are proportional to n-1. So these dots indicate the Qmax at a given mass square. Now to the two curves. Firstly, the solid blue curve passes through the origin and gives a well-defined, unique charge to mass ratio value, which will be our reference ratio value for the extremality notion. Then any dots sitting strictly above this blue curve, anywhere here, will imply that there exist certain super extremal states with respect to this reference ratio. Note that there are quite a few dots in the upper region. Some of them are in fact sitting precisely on this dashed red curve. So I color them red. Once again, these red dots are special because they imply super extremal particles with the corresponding charge and mass. Very interestingly, we observe them at any charges that are multiples of 4, and this is never a coincidence. Because the elliptic genus is a Jacobi form, due to the so-called theta expansion property, it is guaranteed in any 60 F3 EFTs that for every charge on this sublattice of index 2m, there is a dot sitting on the red curve, and in particular, strictly above the blue curve. And this leads us to the other two constraints. The completeness just immediately follows from the expansion terms in the elliptic genus with arbitrary powers in Xi. The weak gravity conjectures have also been confirmed in a sense already. What we've seen is the following. So at every charge value on this sublattice, as illustrated in the example, we have states on the red curve at this corresponding mode number. Then carefully keeping track of all the numerical factors, we conclude that the charge and the mass of these sublattice states obey this equation. And in particular, this inequality of the conjectured form is obeyed with the model independent lower bound mu equal 1, which is precisely the reference value computed from the blue curve. For all of this to work out, what turns out to be very crucial in geometry is this relation amongst the various volumes in the weak coupling limit. So it's the volumes of the heterotic curve C0, the U1 divisor B, and the internal space B2. We could indeed confirm this geometric relation in all weak coupling limits of a general 60F theory. So what about in 4D? Having detailed the 60 story, I will just give a very brief 2-slide summary of how it works in 4D before concluding my talk. Maybe it will take a couple. Yes.
Sorry, excuse me.
Yes, yes.
Perhaps I should know this, but so this hydraulic string is from this raptor D3 plane, right?
Yes, that's right.
And the U1 is on D7, is came from the D7 plane.
Yes.
So in terms of the excitation of these D3 branes, is this U1 is not a global symmetry?
Yeah, so the world will view this U1 as a flavor symmetry indeed. So that's why I was talking about Toft anomaly.
Okay.
Yeah. Okay.
Okay.
So, yeah. Is that okay?
Yeah, I'm just confused because this weak gravity conjecture thing is for the gauge theory, right? It's for the gauge, yeah.
Yeah, so okay, so very good, yeah. So in the space-time point of view, it's of course gauge theory, but in the worldsheet point of view, it is a flavor symmetry, and I'm using some calculation results from the worldsheet side to say something about the space-time. That's the logic.
Okay, I see. So one can also say I go to the heterotic dual
so I'm looking at the heterotic dual theory.
Okay,
yeah.
Good. Thanks.
So very quickly, recall that for special fluxes of a quasi-modular type, the 4-dimensional heterotic elliptic genus was a genuine Jacobi form, and therefore the theta expansion, which was crucial in the 60 story, still guarantees, again for the same reasoning, the super extremal sublattice particles. Now, for general fluxes, that's the question. We have had 2 lessons from part 1. One is that the 4-dimensional heterotic elliptic genus is not Jacobi, which is unfortunate in general. However, the other is this very good news that the way the Jacobi property is lost is rather mild. Our proposal, if you recall, was that the elliptic genus is a sum of a genuine Jacobi form of weight -1 and a derivative of another Jacobi form of weight -2. You may think that the derivative part is potentially problematic in realizing sublattice particles, but in fact, it's still fine. The reason is the following, very quickly. First, the weight -2 object by itself does have super extremal terms by the Jacobi property, which was precisely the 60 reasoning. Secondly, the role of Xi derivative was just to multiply each non-trivial term in the z -2, m by the charge r. Then obviously any charge, the super extremal terms will remain after the derivative. Therefore, the sublattice version of weak gravity should still work out. Now, On this final slide, I wanted to quickly flash through 3 new physical features in 4 dimensions. So let me very quickly give these comments. So firstly, unlike in 6D, the 4D F3 in general suffers from quantum corrections. In other words, any classical geometric results have a danger of being corrected. Recall that what's crucial for weak gravity was this volume relation in the weak coupling. We have confirmed this at the classical level in a general weak coupling limit of any elliptic Calabi-Yau 4-fold, which was already non-trivial. What we've checked next is then that, actually, this classical relation in the limit survives the corrections, which is even more non-trivial. And secondly, in 4D, the U1s are generically Stuckelberg massive. So what we've generally shown is, in fact, that the weak gravity still works for Stuckelberg U1s. However, I should also say that for the special quasi-modular fluxes, the Stuckelberg mass turns out to be effectively 0 in the weak coupling. It just turns out to be so. So our logic also covers long-range forces as well. And finally, in 4D F theory, a U1 may arise not only from non-trivial sections, but also from breaking a non-abelian algebra by a flux. But even in this type of U1s, the weak gravity can still be explained in much the same way, except that we have to now rely on different types of Jacobi forms. And this brings us to the conclusions. Instead of reading this for you, I will just stop here. Thank you very much.
Thank you very much for the talk. Are there questions?
So can I ask you some questions?
Yes.
Yeah. So first of all, my first question is, so in all your elliptic genera, you only consider the elliptic genera wrapping the very low base degrees, like wrapping only the curve once or twice, maybe?
Oh, that's right. Okay, that's a good question. Yeah. So that's right. Yeah. Mm. So,
but why don't you consider like elliptic genera of higher base degrees?
Good. You could do that. If you do that, then of course, as you may know, there is this there is some discrepancy between Gromov-Witten and BPS invariants, and I mean, one can work out this link, but here, well, computationally you can do whatever. You can still do so. I was only looking at this because I was only interested for this part 2 at least in the excitation spectrum of the heterodic string. So I only wanted to look at the elliptic genus of the single heterodic string. But you can, of course, do arbitrary, even non-critical string, even multiple strings. The logic will still work out. Here, I only focused on the single string and mostly on heterodic string.
But for multiple strings, does it have some implication in the weak gravity conjecture? Or? So
I think only for the heterodic, you can say something about the physical excitations in the spacetime, because that's where you know how to quantize strings. Non-critical strings, you can think of it as some 2-dimensional string theory, but you don't know how to quantize it in the spacetime.
Okay. Maybe sorry, I have another question.
Yep.
So in a setup of Calabi-Yau 4-fold, and you have the 4D effective theory.
Yes.
So can I say that given 4D effective theory, you have the ansatz for the denominator of the genus?
Sorry.
I mean, so you have the ansatz for the denominator of genus.
Oh yeah,
Is that right?
Yes. That was the eta to the power, yeah.
But I mean, so if you consider more complicated effective theory, do you also have some universal denominator?
So here the denominator I gave was eta to the
right.
Yeah. The k bar times the curve class.
Right.
And we propose that this will work for anything, just as in 6D.
But in 6D, if you have some gauge groups,
yes,
and this denominator will be more complicated.
Oh, sorry.
Yeah.
So I was, okay, thank you.
Yeah.
So I'm not looking at instanton strings here. I'm looking at strings that, so D3 that transversally intersecting with the D7 in the internal space. We have also looked at an instanton string also in our recent paper. And there it's going to be very different. The structure will be really different. Yeah, yeah.
I see. I see. Okay.
Here I was focusing on the other type. Yeah.
I see. Okay. Okay. Sorry. And by the way, I have a very naive question.
Yes.
So why your elliptic genus has a non-zero weight?
Oh.
You rescale the elliptic genus, or you divide by something?
Didn't you divide by center of mass?
Yeah, precisely. Yeah.
Okay. Okay.
If you include that, it will be degree 0, right?
Okay.
Yeah,
okay.
Weight zero.
Weight is zero. Yeah, that's right. Yeah, precisely.
Okay. Okay. Yeah. Okay. Thank you. Yeah.
But a related question is that,
Yes.
I mean, since you computed elliptic genus with center of mass factor, this space-time motion mode excluded, if you consider multiply winding strings, I mean, they have very complicated bound state structure, right? I mean,
Yes.
multiply wound strings can have a direction of moduli which can be separated into two unbound strings, and this threshold bound state issue is very complicated, right?
Yeah,
so can you sit down and just compute the multiple round strings, or
we could do that. We just didn't have enough energy to go towards that direction yet.
And you're computing, and in that case, are you computing both unbound states and bound states?
So
it's depending on whether you count bound states or not, the center of mass factor that you have to factor out will be different.
Right.
So I was thinking, I mean, it's quite challenging thing. I mean, what would be the starting point?
Right. So
in other words, if you're just insisting on counting bound states only, maybe that.
Yeah, I think that's what we'll give.
Mass modes.
Yeah, I think the Gromov-Witten side will tell us about that.
Just bound states only.
Yeah, bound state.
Okay.
Yeah, I have a related question. So
yes.
I think you considered only the curves which give rise to the curves in the base, which gives rise to the heterotic string, right?
Yes.
Then does heterotic string form a bound state when you consider?
No.
So there is no multiple.
No, I was when someone was asking, I was thinking more of these strings in 4D.
Yeah. For heterotic strings, you just computed one string, so there's no such issue.
Just Hackett transform. It's just trivial thing. Yes.
Okay. Yeah. Another question is, you said that you also considered instantaneous strings to bound the bulk gravity. How can instantaneous strings either some constraint? How does this instantaneous string can see the bulk constraint?
The bulk constraints.
Bulk hypergravity constraint.
You mean sorry, in the effective theory or
effective theory?
No. So the purpose of looking at the instantaneous string was to make sure our setup is correct about this proposal, derivative structure, all of this. So we just checked this in order to make sure that this structure persists even for instantaneous strings, and it works.
I see. You're not interested in constraining.
No.
Okay.
For pure curiosity, we check this. Yeah.
Okay. Thank you.
Seung-Joo, can I ask you a question?
Yes. Hi.
So it's about the derivative sector. So the xi d by d xi derivative breaks the Jacobi property, of course. Is there a canonical? I think the answer is yes, but is there a canonical way to covariantize this derivative by forgetting holomorphicity in xi? And if so, what would be the physical interpretation of performing by hand this correction?
So I didn't want to talk about it. So we are working on it. So as I said, there is this nice story. This nice trade between holomorphic anomaly and modular anomaly.
Right.
And we are seeing something, and then we will show it very soon.
Okay. Yeah. Maybe we should discuss a bit more about this, because from the purely geometric elliptic genus, you can also perform this exact trade-off between holomorphicity and Jacobi property, and I cannot really understand the physics behind that. So I would be very interested to understand more. Okay, thank you.
Okay. More questions?
Yeah. So in your case, 4-dimensional string case, rest of space is compact.
What space is compact?
The rest of space, besides 4-dimensional, like 6-dimensional is compact.
That's compact. Yeah, that is compact. Yeah.
And then your string, is it charged in 4-dimensional or is it neutral in 4-dimensional?
It is charged.
but then flux coming out of this like logarithmically divergent, so you cannot have a well-defined physics vibration. I mean, 60 is possible because the flux is localized around the flux and the string, but because you have only two transverse directions, if you have flux coming out, then you know, potentially it's log divergent. So I don't know how to define elliptic genus in physics.
Sorry, I was saying it's charged, but it's, I mean, I'm talking about, so what I mean is that this D3 brane transversally intersects with the D7 brane. And in this sense, it is charged under this U1, but I'm not talking about, this is a gauge field, right? One form field.
Yeah, so let's see.
I'm not talking about any two-form field coupling to this string. Here, I'm just naively
being charged under one form will be more dangerous, right? Because it's just
maybe charged is not the best word to use here. I'm just saying that these Fermi modes between 3 brane and 7 brane are localized on this string. That's all I was meaning by saying it is charged.
The 6-dimensional U1 reduced to 4D, is it still dynamical gauge field?
6-dimensional U1?
The dynamical vector field? I guess so.
What's the 6-dimensional U1 here?
Yeah, 6-dimensional U1. It's a 6-dimensional dynamical vector, right?
So are you talking about the 60 story of mine or 4D?
Sorry. You're not reducing 6 to 4.
Yeah.
So it's a 4-dimensional dynamical vector?
Yeah, it is a 4-dimensional dynamical vector in the external spacetime.
Yes, then the worry that Kim Young raised is very relevant, right? It's a co-dimensional 2 charged object because it's a string, right?
Yeah.
It is charged. Well, I mean, string can only be charged under a 2 form, right?
No, but you intended to.
You were thinking of U1 charged elliptic genus, right?
That's right. Yeah. So it's global symmetry for the worldsheet theory. Yeah.
Well, but in the bulk, it's
gauge symmetry. Yes.
It's gauge. So then, as Kim Young said, a co-dimension 2 object which has gauge charges, I mean, having infinite inertia, right? It's a logarithmically divergent Coulomb potential and so on. If it's macroscopically extended along a line. I guess that's what he meant.
Yeah, that's what I mean. That's why it's difficult to consider, for example, monopole string in 2D because it has, so log divergent energies. So I don't think elliptic genus is well defined. If we vibrate, everything will disappear.
So maybe I'm not sure if this helps, but in fact, this U1 gauge field is a Stuckelberg massive, and it is just the mass scale that can be parametrically smaller or similar to the energy scale.
So it's Stuckelberg mass also in 4D?
Yeah, also in 4D.
So it's slightly Higgs or something.
Yeah, I mean, it's getting mass via Stuckelberg mechanism. Not like Higgsing, but it is yeah. So maybe this might help, but yeah, I haven't actually thought about it that way.
Okay. Okay. Other questions?
Yeah, I still want to go back to these quantum corrections. I mean, in the 4th dimension, you have a super potential, right? And
I actually don't have anything to show you here, but yeah.
Okay, I'm just saying, in 4D, there's a super potential. For example, you can form these D3 instanton, and it might be it might be abstract to you to go to such limits, infinite distance limits.
Okay, so yeah, so here it is fine. We will have things to say, but yeah, it is going to come out soon. But yeah, you can still go to the limit.
But you can still go to that limits.
Yeah, I think so. Yeah.
But have you calculated the super potential?
So we are looking at it right now.
Okay.
Yeah.
Okay. Since people need, I guess, a little bit of rest before the next talk, so let's wrap it up here and thank the speaker again.